Okay, so finally it's time to talk about the equipartition theorem. So I'm just going to say it can be shown that, thought about having you guys do this problem, but it's pretty hard. It can be shown that for every quadratic term of position, so like x squared in the harmonic oscillator, for example, or momentum, so like the momentum squared term in the kinetic energy in all of our Hamiltonians that we've had, a contribution of kT over 2 is made to the internal energy of the system. This is the equipartition theorem, and it is something that can be derived just using statistical mechanics. But we'll take it as a given. But this only applies to degrees of freedom that are in the high temperature limit. So we talked about the high temperature limit for rotations. We know it's also true for translations. I don't think we did an example, but the translations are the easiest degrees of freedom to excite. And we showed last time in class on Friday that the rotational temperature is less than 1 degree Kelvin typically. But what about vibrations and electronic excitations? Are those in the high temperature limit? And remember, the high temperature limit is that temperature at which you can replace the sum in the partition function with an integral. So in other words, the energy levels are so close together that you can integrate. But it has this real world then application. So in general, and again, just take this as a given for now, and we'll talk more about it in a minute. But translations and rotations, the high temperature limit is okay. But vibrations and electronic degrees of freedom are probably not okay, except for some sort of specialized situations. So the implications are pretty cool, actually. So going back to Chem 317, and whether you took it or not, just know that, for example, the constant volume heat capacity is the first derivative of the internal energy with respect to temperature. So if we can just know, okay, for every quadratic term we get a kT over 2 in the internal energy, then we should be able to get the internal energy and the heat capacity. So for example, for a monatomic ideal gas, so argon or any, could be xenon, helium, whatever, the degrees of freedom are just the three translations. There's no rotational degrees of freedom for these spherical atoms. So the internal energy is just 3 times kT over 2, or 3 halves kT. So you know the internal energy of any atom. Bam. There it is. It only depends on the temperature. And so we can find CV as well. You can take the derivative of this, the temperature disappears, and it's 3 halves K. 3 halves K is the constant volume heat capacity for a molecule of an ideal gas. Or if you want a mole, 3 halves R, just multiplied by Avogadro's number, because of course heat capacity is an extensive property. So that's simple. All ideal gases have this as their constant volume heat capacity, and that falls right out of the statistical mechanics. Now, if you go to a molecule that isn't spherically symmetric, so for example a linear molecule, you'll have rotational excitation in 2 out of 3 dimensions, like every dimension except for the axis. So your degrees of freedom now are 5, because you have 3 translational, 2 rotational. And we're just ignoring vibrations for now. So then just from translations and rotations, you have 5 degrees of freedom times kT over 2, so 5 halves kT, so the CV would be 5 halves K for a molecule, or this should be 5 halves, not 5 fives. 5 halves R. For a nonlinear molecule, now you can have rotation in the 3rd dimension, so your U is 3 kT and your CV is 3K, or 3R. Pretty cool. Okay, now what about vibrations? So it can be shown that the high temperature limit works for vibrations when the temperature is equal to 10 times the vibrational temperature. And this is very similar to the rotational temperature. Basically, you have your eigenvalue here divided by K. Oh, this is the gap between your eigenvalues, h nu over K. So 10 times that. So for example, with a fluorine molecule, here's your wave number between levels, and they're evenly spaced for the harmonic oscillator. So then your temperature is 10 times plugging in numbers, and you get a temperature of 13,190 Kelvin. That's pretty hot compared to room temperature of about 300 Kelvin. And in fact, it's twice the temperature on the surface of the sun, or a little bit higher than that. Surface of the sun is about 6,000 Kelvin. So, nevertheless, if you do get temperatures that high, maybe at a specific point in a reaction or explosion or something, then yes, we would contribute 2 times kT/2 per mode. And why is it 2? Well, if you remember, the Hamiltonian for the harmonic oscillator still has a kinetic energy term, but then it also has potential energy term. So it should have 2 contributions of kT/2. But you can only use that at extremely high temperatures. Okay, how about electronics? So the electronic partition function, again, it has the same form as before. I just sum over all the states with the degeneracy in there. So for example, with the hydrogen atom, here's our eigenfunctions. And if you figure it out, all of these constants together is negative 109,707 inverse centimeters. And the ground state is 1, and we go up from there. And the degeneracy is 2n squared. So, 2 electrons fit in 1s, and 8 electrons fit in the n equals 2 level, right? 2s2, 2p6, so etc. All right, so here's the different spacings for the different levels. And you can go up from there. And basically the Q is going to be all of the electrons will be in the ground state for basically any temperature, because if we look at the electronic temperature, so the first excited state divided by Kelvin, it's 118,000 Kelvin, which is a huge temperature. So almost all atoms and molecules will just have the Q be equal to the degeneracy. There will be some exceptions. So for example, if you have like a dye molecule or something that's photochemically where the lowest unoccupied orbital is really close to the highest occupied, then you can get some electronic excitation. All right, so basically as far as equipartition goes, it doesn't work well for vibrations or for electronics. All right, one other thing I want to say about vibrations. The partition function for vibrations is kind of special because there's going to be, the easiest way to treat it is to have a partition function for each vibrational mode. And how many modes will there be? Well, we know from before, for a linear molecule, it's 3n minus 5. Nonlinear, it's 3n minus 6. So, for example, carbon dioxide is linear, so 3n minus 5. 3 atoms, so 9 minus 5, so 4. But then, one's a symmetric stretch, one's the asymmetric stretch, but then 2 are degenerate with each other, a bend in and out of the plane. So the total vibrational partition function will be the product of these 4 partition functions, but because these 2 are the same, then we can just have them squared. So the total partition function for carbon dioxide, you'd have product of all the partition functions, translational, rotational, vibrational, electronic, and then you can split out the vibrational in this way. All right, that's it for today. I hope that you turned in your problem set already, and I'll give you some details about upcoming things in an email.